Let's start with number 9. A deuteron, not sure how to pronounce that, with the same charge but twice the mass of a proton, that's just what this particle is moving with a certain speed perpendicular to the field, so we know it's going to experience a force. And we learned that if it's moving exactly perpendicular to the field, then that perpendicular force will be a centripetal force that will cause it to move in a circular path. So we know it's a circular path. We need to know, well, how big is that circle going to be? And that is simply going to come from using the same equation that we used back in number 2. That gives us the radius of this path here, mv over qb. And we plug in the numbers. So what do we have here? We have the masses given right here. The v is right here. The q is the same charge as a proton. So q is 1.6 times 10 to the negative 19. And then b is right here, 0.2. Plug and chug. And we should get about 0.031 meters, which is 3.1 centimeters. So the way that the answer would have been a straight line path is if it were moving parallel to the field, then it would not experience any force. So then it would just keep going in its straight path. Number 10. Here we have 2 wires carrying a current in the same direction. What's the field between the wires? So this is very similar to number 3 that we did earlier, but number 3 we didn't have any numbers. And in this one we have numbers. So the currents are in the same direction. And I1, I2, so this is going to be I1 is 10 amps and I2 is 20 amps. And want the field halfway between them. They're 40 centimeters apart, 0.4 meters. That means that R, the distance, is going to be half of that, 0.2 meters. And we know that each field is going to be given by mu I over 2 pi r. So the r's are the same for both. The currents are different. Mu is that permeability of free space. You're going to plug in mu is 4 pi times 10 to the negative 7. And unfortunately I didn't calculate the numbers, but you're going to get 2 numbers. And they're going to be different because the currents are not the same. But then what's important is to find a net field is you need to know, once you have these 2 numbers here, are you going to add those numbers or subtract them? And that depends. If the fields are going the same direction, then you're going to add them. If they're going in opposite directions, then you're going to subtract them. So let's take a look. So let's ignore I2 for a second. Let's just look at I1. If you use the right hand rule, the thumb is in the direction of the current, your fingers are curling. Your fingers are curling out of the page to the left and into the page to the right of the wire. And all we care about is to the right of the wire because we care about a point halfway between. So we don't even care about this. If you look at I2, once again, to the left of this wire, your fingers are coming out of the page. To the right of the wire, they're going into the page, but it's not asking us about the field over here. It's asking us about the field here in between. So they're in opposite directions. So that means that you're going to subtract these 2 numbers. When you subtract these 2 numbers, you'll get A. So you can think of it as you're adding these 2 numbers, but you made one of them negative. It doesn't matter which one is negative, because it's just by choice. You can choose as long as you're consistent. The question is just asking us for the magnitude. So you'll get a positive number. If you got a negative number, then just find the absolute value. That gives you the difference between the two numbers. Number 11. So we have another one with the force between two wires, but this one has numbers. So the force per length between two wires is given by mu I1, I2 divided by 2 pi d. D is the distance between them. These ones have currents in opposite directions. So, first of all, what is the force? Well, the force per length is this. Since we have the length, we can actually solve for the force. Just multiply both sides by L, so that we can get the force by itself. So we have currents I1 and I2 here. They're both 3. Those are I1, which is I2. Plug in mu, defined up here. Your length is right here, 0.5. And then the distance between them is right here. So plug in all of those numbers, and you should get 1.8 times 10 to the negative 4. And then it's a matter of knowing if the forces are going to be attractive or repulsive. We learned that if the currents are in the opposite direction, then the force is repulsive. And I never really memorized this until recently, because I've just done it so many times, but you can always derive it if you forget. The reason that there's a force on these wires is because, for example, this wire over here is in the magnetic field created by this one. So if you do it one step at a time, this wire going down, with the current going down, is creating a magnetic field. To the left of this wire, the magnetic field is going into the page. It doesn't matter if you're this far to the left or this far to the left. This is a magnetic field. Both of these arrows is a magnetic field created by this wire. I'll even erase the other wire for now. If you're to the right of this wire, the magnetic field goes out of the page. So this wire is creating a magnetic field. And now you're putting the other wire into this field. So this wire with the current going up is finding itself in a field going into the page. What's the direction of the force? You put your fingers up for the direction of the force. So you have your fingers up. And then you're going to fold them in the direction of the field. That means you're folding them this way. I'm trying to show that they're folded into the page. It's kind of hard to draw. And which way is the thumb going? The thumb, if you do this, is actually going to be pointing to the left when these fingers here are going into the page. So the thumb is the force. That force is to the left. So that's how you know that this wire experiences a force to the left. You do the same thing for this wire. It would experience a force to the right. And that's how you know that the forces are repulsive. The last one here is a solenoid. What's the field inside the solenoid? This is a plug and chug. That the field inside a solenoid is given by mu n I divided by the length. And we're given 500 turns. That's the number of turns n. The length here is going to be converted to meters, 0.5 meters. The current is 10 to the 4th amp, so you get a huge current here because it's a superconductor. It's something that has very little resistance that can carry a large current. So you've got your I here. So plug in these 3 numbers and the mu that we defined earlier. and you should get 12.6 Teslas.